Good evening. I'm Tom Rosenbaum. I'm president of Caltech, and it's a great pleasure to welcome you here tonight to our campus. This is a very happy occasion. Franklin Delano Roosevelt observed that happiness lies in the joy of achievement and the thrill of creative effort. In Voyager, we have 40 years of joy and thrills. After collecting bumper stickers from the giant planets of the outer solar system, Voyager 1 exited the heliosphere and is now hurtling along in interstellar space. It has given new meaning to the notion of, are we there yet? The beauty is that even at almost 19 billion kilometers away, almost 16 billion kilometers for Voyager 2, there are no boundaries. There is always more to learn and continuing inspiration. We celebrate this evening the joy of achievement and the thrill of creative effort in two significant ways. We will hear from the men and women of JPL, Caltech, NASA, who played an essential role in imagining, realizing, and analyzing the Voyager missions. We will encounter as well continuing inspiration through the majestic efforts of the filmmakers of HHMI and PBS, which is where we start with a special screening of the Farthest, Voyager in Space. Enjoy.
What a great film. Take a bow, you guys. Stand up and take a bow.
Those are all the people that work on the project out there.
Yeah. Oh, thank you. Thank you.
So, really, congratulations to anyone who had any part of that film and the people, the stars of the show here. You guys, that's a very moving experience. It really is. And after all these years, I'm still bothered. Why did they launch Voyager 2 first? Why?
I think Charlie's out in the audience, so he can explain.
So, you know what? I'll tell you what. I want to start with Susie. When was the last time you checked in with the Voyagers? How they doing? They still phone home regularly, right?
Yeah, the Voyager spacecraft, both of them, contact us every day.
How are they doing?
They're doing great. They're as healthy as senior citizens. And,
do they have insurance?
Oh my gosh. Intergalactic Obamacare.
Yeah.
So, yeah, broad coverage. So, is there much science to be done right now, Ed? You know, by the way, there's only one and only project scientist for Voyager for 40 years and going now, and this is the man right here. He's really not so much a stone as he is a rock of Gibraltar. So, and here he is. Is there science to be gleaned still? What are we learning?
Voyager 1 is in interstellar space, where it's really now measuring what the galaxy is like rather than what our own solar neighborhood is like. The sun creates this huge bubble around itself. All the planets are inside that bubble, and only Voyager 1 is outside. We hope in the next 2 years, Voyager 2 will also join Voyager 1 in exploring the nearby interstellar region of space.
So when they pop through that barrier, is it like the sound barrier, or what happens?
We have a very sensitive detector that tells us we've gone through, but in fact, it's basically a vacuum as far as the spacecraft is concerned. It's unaware that it has left the bubble, but our instruments know.
Susie, you were saying it's kind of like having a very far-flung weather reporting device, a meteorological station, kind of.
Yeah, it's like flying a weather station through both our heliosphere and also with Voyager 1 in interstellar space. So the spacecraft is out there sensing the environment that it's flying through.
So let's talk a little bit about some of the great moments on Voyager. Watching the media there gathering, you get the sense in a very concrete way of what a communal event the whole thing was. And I always tell people that I love covering space because it brings people together. We talk about moments we remember. Where were you when they walked on the moon, et cetera. This is those kind of moments. And what was it like being, Carolyn, on the inside of that?
Well, you can imagine it was incredibly thrilling, and I had this incredible sense of privilege that I was one of the people who was part of this. And I got added really late. I got added right out of graduate school after Saturn encounters. So I got added for the Uranus and Neptune encounters. And it was like someone just grabbed me by the hand and took me off on the most incredible journey adventure that humanity had ever undertaken. So that was just always with me, that it was just such a privilege. But there were some just tremendous moments. First of all, as you said, the press conferences were a delight, because the press always asked really good questions. You remember Jonathan Eberhardt? He kind of added a Socratic air to the whole thing in the way he'd ask questions. Mm-hmm, mm-hmm. And it was the interchange between the scientists and the press was wonderful to listen to. But I remember a really special moment after Titan flyby, after the first Titan flyby, Voyager 1 at Saturn. And I guess the radio science team, for a brief period of time, thought that the conditions on the surface of Titan would admit the possibility of liquid nitrogen. Do you remember this? Mm-hmm. And it went around like a rumor throughout the halls and the rooms in Building 264, where the science teams were gathered, like, oh my God, there's liquid nitrogen on the surface of Titan. And for a moment, I felt like Building 264 was like the Starship Enterprise. And we were hovering above Titan, reading signals. And we had just come upon this alien planet that had liquid nitrogen on the surface. It was things like that that happened during Voyager.
You know, space does that. You know, we sprinted to the moon in a race to beat the Soviets, and then ultimately we all kind of went together, didn't we? You know, it does bring us together. And take us inside a day in the life of the project scientist in the midst of one of these frenetic flybys. What was it like trying to feed the beast and herd the cats of scientists and then dispense all of this to the public? There was a lot going on.
Yes, there's a lot going on, and that's one thing that made it great for all of us. In that sense, science is about learning new things. And in this case, it was every day there were many new things, and we would know that no matter what we knew today, we would know more tomorrow. It was really, and one day, it was day by day by day. And one thing which we did is because one of the challenges scientists we have is how to have peer review of what we believe we know. And that's done very carefully through publications and so on. But I felt it was important, because of the interest of the public, to bring them along with our discovery process. And so we had peer-reviewed science discussions every afternoon, and overnight the graphics were made, the images were produced, and other graphics for the non-imaging instruments were produced for the 10 o'clock press the next morning, next afternoon, next day. We were really built into the process of understanding the science we were doing collectively, not just each individual, but collectively, and engaging the public along the way.
All without sleep.
And no sleep. So you can imagine how this went. So instantaneous peer review, scientists just love that,
yes,
right?
Yeah.
And I'm sure there were no arguments at all, right? Give us a sense. Was it heated? Was it? I mean, because there was tremendous excitement, which buoyed you through this, I know. But did it get tense?
It's tense in the sense we knew that there was a lot we didn't know. But I think that the team was really working well, because we have to, you see, before any encounter, we had to design the sequence of observations. That was all determined ahead of time. And already the science team had become much more integrated, because they had to integrate the interests of all the teams in a reasonable way for the mission. And I wouldn't say there were big arguments. There were different interpretations, but that's what science is about. And eventually you'll sort out by observations which is the correct interpretation.
Well, I think a little bit of that is that's what Ed Stone is about. You did a pretty good job
Did a great job.
herding the cats on a speeding train, to mix metaphors. But tell us a little bit about, you observed him as the two of you.
Certainly did.
How did he manage this mess? Because this, this could have really gone off the rails.
Okay, so I'm just going to embarrass you, Ed. I think the whole shtick of Voyager, which was this wonderful scientific voyage and trying to understand what we were seeing and trying to, just piece the whole thing together. And it did, I think you're being gracious, Ed, I think it really did get to the point where people were battling. I mean, they went up against each other for resources. And Ed was the one who had to adjudicate and figure out which instrument to go with. Well, am I going to go with this PI who wants to use this particular point in the timeline for his observations, or am I going to go with this other one? And you could imagine that the person who lost would have felt really bitter, right? But it turns out that Ed was just so gracious to everybody and so interested, genuinely interested in everybody's results that Brad Smith, who was in this film, once told me that people didn't respect Ed, they loved Ed. And even when two PIs went up against each other and Ed said, well, I'm sorry, you're on and you're not going to be, the guy who lost thought, well, if Ed decided that, it must be the right answer. Yeah.
The powers of persuasion, right? It's kind of remarkable. Susie, did you witness stuff like that?
I was not, when I got on the project during the Uranus and Neptune timeframes, I was not so involved with the science teams directly, but I do go to the science team meetings now with Ed. About twice a year we have them, and they're wonderful. These people have worked together for 40, 45 years, and they
like
still—
an old marriage.
Yeah, like an old marriage, exactly. They still banter back and forth. They can remember, things that happened 30 years ago and bring it up if they need to. But you never
No
let
hard
my
feelings,
instrument
but
turn on,
in 1979, you son of a,
Exactly, that's exactly how it is. But I still think that there's definitely a respect for Ed in the room amongst the scientists, amongst his peers and his colleagues, and honestly, he's just a remarkable man. I love working on Voyager. I love working with Dr. Stone. He shares everything he knows, and he's very gracious, as Carolyn added.
Well, so Ed, and we've sort of danced around this, but can you remember, was there a real Donnybrook along the way that you remember you had a really hard decision to make on which sensor to point at which time, and was there anything that stands out in your mind that way?
Yeah, well, let me just pick the last one of those, the one that had to do with Triton. This is the moon that was, we had to go over the top of Neptune down to Triton. And the challenge we had was we had two different ways of observing the effects of an atmosphere at Triton. One is to watch the sunset in the atmosphere on this little moon, and the other is to watch the radio signal from Earth to disappear. And it turns out the aiming point for the trajectory was slightly different for those two cases. And we could make it 100% sure that this would work, and then unlikely the other one would work, or 100% that one would work, but not this one, or we could go 70-70. I went 70-70 because I felt we both really needed both kinds of measurements because this is totally unknown what we were approaching. Fortunately, it worked.
That must have been a tough call, though.
It was, yeah. But I think the real point is that this is all done very openly, and everybody, that's the reason I think people could accept the decision, because they actually understood the other part. It was also a very important thing to do, and somebody needed to make the decision. By the end, I didn't have to make very many decisions because the team made them themselves after that. I mean, they began to be much more integrated as a team with each encounter.
One notable thing about Ed that I remember is that he'd go around with these notebooks, these old, at least when I went to school, these black and white marble notebooks, hardcover.
He still uses those.
Oh. He still uses them?
Yeah.
It's this thing you put ink on paper.
Yeah.
It's an old thing. It's useful.
He used to go around with these notebooks and he'd talk to everybody. He'd talk to the PIs, of course. They're the important people, but he'd talk to everybody, even the lowly graduate students like myself at the time, and one asked you, what are you working on? And, oh, that's so interesting, and he'd be there jotting in his notebook, and he must have 150 of these things.
So
But,
did you,
I mean, he did his homework. That's why
did
he
you
was
ever-
able to make good decisions. He did his homework.
Did you look at the composition book and it said milk, eggs, meat?
Oh, I did.
Do you have all those notebooks? Those would be a real treasure trove, I think.
Yes, I do, and I occasionally look at them when I'm trying to remember exactly what we thought we knew when. Because I started these because I realized we were on a journey of real exploration, and that you can't recover after the fact what you thought you knew. Because once you learn something new, it's hard to go back and think about it before you knew. And so I decided I would record why we made decisions, what we thought we were doing, and then when something happened, we could reflect back as to whether, how that worked out.
Now, I'm embarrassed. Have you ever put this in a book? Have you ever?
No.
Well, we got to get busy. All right, so.
You should archive those in the Library of Congress.
Absolutely,
Yeah.
absolutely. All right, so I know these are unfair questions, but there's so many images to choose from. But whether you call them your favorite or most scientifically significant, probably maybe that's two different categories. I'll start with you, Carolyn. What would it be?
Okay, so one of my favorite images is the image that was on the television screen as Voyager 1 was pulling away from Saturn. So this was the one, as you heard, it went above the...
Oh, you see the shadow, that one? The
and
one
you see the shadow and so on. And I just remember being alone in a room at JPL. The madness of the encounter was over. Everyone had gone home. And I'm in this room. It's just me and this monitor. And there's coffee cups and cigarette butts and, chocolate bar wrappers all over the place. But I'm just, I'm mesmerized by the sight of this picture and thinking about what had just happened, not only to humanity, but to me, that I just had participated in this thing. And I, fell into this reverie about the whole thing and how glorious and grand it all was. So that picture has a lot of meaning for me. Another favorite picture, even though at that time I was a ring scientist studying rings, another picture that I thought was so fabulous was a picture of the Neptune atmosphere where you could see the white clouds. And they were three-dimensional. We had never seen three-dimensional clouds. It was the first. No one's ever made a point of this, but it really made an impression on me. So those are the two pictures that come to mind.
Susie, do you have a favorite?
Yeah, it was in the movie, actually. It's the one that shows the crescent of Neptune and Triton.
The goodbye.
The goodbye image. And I was the lead sequence integration engineer for Neptune Encounter. So I sat with the scientists. We designed the image, both that one not so much scientifically, but more for the effect. And it certainly has the effect. Voyager is saying goodbye to the planets, and it's going to continue off around the center of the Milky Way galaxy.
Ed, what about you? That's got to be a tough one for you.
It's really tough because there were so many discoveries made. But I guess from one sense, one which captures things for me is there's one image which shows, and I think it was in the movie, but with Jupiter, you can see the great red spots, you can see all the white storm systems, you can see Io and Europa, because those two moons, first of all, the dynamics on Jupiter were just spectacular to see the atmospheric dynamics. But Io, of course, was before Voyager, the only known active volcanoes are here on Earth. And here's a little moon with 10 times more volcanic activity. So that image, of course, is, I think, really iconic. The one of Jupiter with Io and Europa there, you can see there's a reddish-orange satellite and the snowy white one right together. And it really, again, was sort of characterized the amazing diversity and complexity of things in the solar system. Everyone has its own pedigree, if you like, and it's different. And there's so much to be learned by seeing all these objects and understanding better how the processes are that lead to what we see today.
So is the great scientific discovery kind of everything in aggregate, or is it the volcanoes on Io, the geysers on Triton?
I think in aggregate, it really is the fact that it taught us that our terracentric view of planets was just much too narrow. It wasn't that we needed a little bit of expansion. We needed an enormous expansion of what the planets are like, what satellites are like, what the solar system is like. That's what Voyager taught us. And now, of course, we know many other planetary systems are on other stars, and they're all different in our solar system. And when Voyager was going, everybody thought our solar system was a prototype of solar systems. No. Every one is different.
You have something to add? Do you want to add?
I think the answer for me, the answer is the aggregate, because if you think about it, whether you talk about the amount of mass that's contained in the bodies in the outer solar system, or the number of bodies, or the volume that's subtended by their orbits, the vast majority of the mass and the bodies in our solar system lie beyond the orbits of the asteroids. So Voyager, in a very real sense, showed us what our solar system was like. It opened our solar system to us. And I think that that's what its legacy is, its scientific legacy is. Other missions have gone deeper, but it just basically opened the door. And that, together with the wistful look at home, the final look at home, the pale blue dot picture, and then the fact that we sent it into the future and across space with this beautiful message that was part of us, really is why it has such a prominence in the minds of the public, and it's in our culture. I think, to me, Voyager is the Apollo 11 of the planetary program. It has that kind of position, and we regard it the same way, and it's because it redefined us. It defined us as interplanetary explorers and now interstellar explorers.
Would you go along with the Apollo 11 analogy, Susie?
Yeah, I always like to describe Voyagers as the grandparents of planetary exploration. You've got the 2 Voyager spacecraft. They were followed up by the children, Galileo at Jupiter, Cassini at Saturn, and very soon we're going to have grandchildren. We're going to have the Europa mission. So I think of Voyager as the grandparents of planetary exploration.
Ed, Apollo 11, is that a good analogy?
I think so in terms of planetary, solar system, planetary exploration. Our place, it's sort of part of our place, what it's like, and it's quite different and much more interesting than we could have imagined just learning from Earth.
So let's talk a little bit about the non-science components of this mission, whether it's the picture of the pale blue dot or the record. Now, a fair amount of this movie is devoted to the record. Did the record kind of bother you, Ed? I mean, you were busy with science. I mean, the record. I mean, how many questions do we have to answer about the record?
A lot.
And here we are, right?
That's right. That's right. No, the record really, the record is not. It's not as though I think it's ever going to be found. It's really a message to us that we were able to send such a message. That's when you think about it, that's quite remarkable. That we have gotten the technology that allows us to send a message into space, into orbit around the Milky Way galaxy for billions of years. It's a message for us, I think.
So you didn't view it as a distraction, or did you wish they were more interested in the ring science at Saturn or something like that?
This is an important part of what Voyager is. It has to do with the fact we can reach out, we can understand things that are around us.
So you're not a scientific purist in that sense. You see the value of the cultural component of this?
Absolutely.
I think the record has really helped connect not just the people in this room who are probably intimately familiar with Voyager, but the whole world with the Voyager, with space exploration. As a project manager, I get emails and interviews from all over the world from people, and they always ask me a question about their gold record. They always ask me when Voyager 2 is going to cross into interstellar space and how long the mission is going to go for. But I think the cultural significance of the record is really important to connect humanity and connect us to science.
I found it very interesting in the movie that there was controversy that Carl Sagan had to call the NASA administrator to get that picture, the pale blue dot, which we all remember so well. in your mission around Cassini as the head imager, you've been like a tourist going to Disney World taking pictures. Did you set, was that very intentional? Wherever you have an opportunity where to snap a picture?
Yes, yes. And, I was on the Voyager project. I saw what happened with the images. And there was not a lot of attention paid to making the images beautiful because they were all done, as you could see. It was all done during press conferences. Planetary scientists weren't then thinking about making pretty pictures. It was all for the science, which was fine, but I just, it was when I became the head of the imaging team on Cassini, I, of course, wanted to add my mark, and I knew one thing that I wanted to do was, first of all, do a good job at presenting the images, in as beautiful a way as I could get away with, without cheating. And I wanted to emphasize true color. We had a lot of criticism on Voyager from one particular person who said that we weren't paying enough attention to true color. So I noted that, I wrote that down in my notebook, true color. Okay. But I also really wanted to use the pictures as a means to bring the public along, take them on the journey with us. And I felt that our job was to be the documentarians of the Cassini mission and to produce the visual record of our travels. So I remember our very first team meeting, I said to the team, we are going to take a picture of anything that moves. Any phenomenon that we can take a picture of, whether it's motions of the atmosphere or it's moons moving or rings changing their perspective, whenever we can get away with it, we're going to do it. We're going to take photo ops, and we did. A lot of times we got away with it, and we have some incredibly beautiful pictures as a result of that.
We do have two microphones here in the aisleways. If you want to approach the mics, that will be my cue that you have a question. We'll work that in. So feel free to join the conversation. We have a few more minutes here. So the sun of pale blue dot is the day the Earth smiled, right?
Yes,
Tell us
yes.
a little bit about that.
Okay, so I actually was one of the people who thought of doing the pale blue dot and joined forces with Carl, who had also thought of it.
So you were like rebels, right?
Well, I didn't get very far. I mean, I was new.
Well, you were no Carl Sagan at that point, right?
I was no Carl Sagan. So, okay, thank you. No, I appreciate it. So I had a different shtick I wanted to emphasize, but nonetheless, I did go around suggesting, we really should do it, and I got shut down. So okay, I went away. I found out a couple of years later, or a few years later, that Carl was also trying to get it done, and we joined forces and we took it. And it's not widely known, but in the proposal that Carl wrote to the Voyager project, encouraging them to do this, because they didn't want to do it. That's why he had to go to NASA headquarters. They didn't want to do it, and to their in defense of them, they didn't want to do it because it required taking the spacecraft off Earth line. That had never been done before. Take the high gain antenna, sever the connection with Earth, take it off Earth line, and the fear was that you'd never get it back. Okay,
that's
so
reasonable.
You can understand that. But Carl eventually got the NASA administrator to instruct JPL to take the picture. And in the proposal that he wrote initially describing this, he put that the idea was to take a picture of the Earth, and I quote, awash in a sea of stars. Well, if you remember the pale blue dot picture, it didn't really have, the Voyager one, it really didn't have any stars in it, and the Earth is sitting on top of a beam of light that was scattered in the optics of the camera. So it wasn't the most beautiful picture, but of course it was the way Carl romanced it, and the way that he turned it into an allegory on the human condition that has ever since made the phrase pale blue dot is, kind of like a call to planetary brotherhood and so on.
All that you know, all that you've done, all that. That was poetry.
Yes,
sure,
it was
right?
beautiful. It was, that was Carl.
Yeah.
Okay, but I knew as soon as I became the imaging team leader on Cassini, I wanted to do that picture over again, only make it better. And somewhere along the line, it turned into, instead of telling people after we take the picture, your picture's been taken, here it is, why don't we tell them ahead of time? Your picture's going to be taken, and go out and look up and smile and participate.
Yeah.
And that's what they did. July July 19th, 2013.
It's a great image. So Ed, let's get you on record. Were you for or against turning the camera back and the pale blue dot? I want to get you on record right now.
Well, I was one of the team that actually met with the associate administrator of Len Fisk, who actually approved the budget to do this.
Oh, so you were in favor? All right.
Okay, eventually, but I think initially you told me no.
Little revisionist history. We want to see the notebooks right now.
Yeah, okay.
Let's get a question in. Go ahead. Thank you. I don't think everybody could hear you. It's particularly ironic given your question. Your question is about whether in fact we'll be able to hear Voyager and whether Voyager will continue to transmit. Susie,
Yeah, I can answer that
tell us
question.
about that.
So Voyager is powered by nuclear power. We radioisotope thermoelectric generators, and we lose 4 watts of power a year. And eventually, we will not have enough power to operate the transmitter. So what's going to happen, the end of Voyager is it's just going to go silent. We could pick up the signal on Earth if the spacecraft could send us the signal. The estimated time for that is probably on the order of the late 2020s, 2027, 28, 29, possibly 2030. We don't know exactly. But if the spacecraft could transmit a signal, we could always get it at the Earth. But unfortunately, it's the spacecraft that's going to stop transmitting.
Well, so Susie, are you kind of nursing it along to try and eke out a little more time, or?
Very much so.
Yeah.
Very much so. And you know, in a couple more years, we're going to have to start turning off instruments. And you can imagine, and I know there's at least one PI out in the audience, and Ed is a scientist as well, but we'll have to start turning off instruments one at a time. And if your instrument's been on for 40 plus years, you don't want to be the first one to go off. So those science meetings are very contested.
Rekindling old feuds.
Yes, right
Interesting.
away. But
Yeah.
it's all about managing power and then thermal considerations, and it's very challenging to actually operate this mission right now.
What is anything being planned for that day when they go dark?
Well, we don't know exactly what day it's going to go dark.
Yeah.
A requiem.
Yes, some kind of a wake or something certainly will happen, yes.
Yeah. Ed, what's it going to be like when they're not sending back a signal anymore for you? I mean,
Well, you know, I think the mission has been so overwhelmingly good that you can't
complain.
You can't complain. I mean, what can you? I mean, after all, this is a 40-year mission already of discovery. We have, you know, maybe up to 10 years more, and I mean, it would have been a great mission with half of that. And so I think I'm not going to be sad in that sense at all. I mean, I think it's
pure gravy, right?
Ed and I are going to get it to 50 years, though. So I expect to invite everybody back in 10 more
I
years.
like that idea a lot. Question over here. Go ahead.
Yes, this is for particularly, I guess, Dr. Porco. Are the images of Saturn's rings good enough that we could translate them into another golden record and play them and see if there's any information in Saturn's rings?
Wow. Wow.
Well,
And if you play it backwards, it says John is dead. Pretty sure.
Maybe.
I'm pretty sure, yeah.
How do I answer? We have, I presume you're talking about Cassini's images.
Any images?
Yeah, okay.
that
Well, we have
are there?
spectacular images of Saturn's rings taken through the Cassini cameras. I mean, it's just been remarkable. I've said this many times that going to Saturn with Cassini and especially looking at the rings was like having LASIK surgery. But for 23 years after the Saturn encounter, we had an image of what Saturn's rings looked like in our heads based on Voyager images. And then we get there and it's familiar, but suddenly there's just all new details and things and so on. So they're spectacular. You're not the first to say, can it be played, you know, like a record? I don't know what the hell it would say. You
maybe
could
it's
try
music.
it. Why don't you try it? Why don't you?
Someone should try this. Why not,
Yeah,
right?
you could try it.
Yeah.
And then maybe Tim Ferriss will produce a record for you and we'll send it into the universe.
All right.
He needs another
Thank
gig,
you.
apparently.
Yeah.
It's another gig.
All right, go ahead. Question.
A number of projects like Voyager today now immediately download their raw data to the internet for citizen scientists to analyze. My question is, would that have been something that you and the Voyager project would have welcomed, and how would it have changed your approach?
Well, today we do provide some basic data that comes in almost, nothing is real time, of course, because it takes light 19 hours to get here. So, but we do put on the web some of the simplest key factors. For instance, the signal which tells us we've left the heliosphere is on the web, and you can see it updated automatically. So it's there. So there is some data, but in fact, the data rate is very low, 160 bits per second.
Well,
Not gigabits,
wow.
bits.
Wow. Yeah, that's kind of mind-blowing right there. But so, but she's sort of, I think she's asking a hypothetical, though. If back in the 70s, you could, I think the first, internet mission was probably Pathfinder, because people got the images along with you all at the same time. Do you think it would have been appreciably different if everybody got the images at the same time instead of what you did, your peer review and then the release the next day?
Well, I think, I suspect, it's hard to judge because it's hypothetical, but I think in the current era, this is the right way to do it. We have the technology to be able to do that. The other thing that it's reflecting back to the 1979 period, that we could get digital images back from space, but there was no way to get digital images across the US. all the communication was analog. No. So you know how we got data across the US digital? Fly it on an airplane.
Wow. Wow. Another question?
Regarding the concept of the solar system bubble, is this a construct that was theorized a long time ago? Is it based on calculations perhaps of the furthest reach of the sun's radiation? And is it conceived of as a fixed place or a movable, depending, for instance, on solar flares and other conditions?
So, yeah, what defines the borderline of the
heliopause.
The heliopause.
Heliopause?
Yeah.
I think that's what he's saying.
Yeah, the heliopause is basically a huge bubble that the sun creates around itself. There's the wind blowing outward from the sun, its atmosphere expanding outward at 1 million miles per hour, and it creates this huge bubble. The place we crossed, the edge of the bubble, was 122 times as far from the sun as the Earth is. In other words, 4 times further out than Neptune, the outermost planet. So that's this huge bubble that we finally crossed back in 2012. And we're waiting for Voyager 2 to follow in the next couple of years, we hope.
But the bubble just stops there? Is it fairly abrupt?
Outside the bubble is stuff that's come from the explosion of other stars, supernovae. So that's the interstellar medium. There's a wind that's coming from a particular direction, which actually creates a tail on our heliosphere. So, but outside, inside the heliosphere, the magnetic field and the solar wind comes from the sun. Outside, the magnetic field is that of the Milky Way galaxy, and the wind is that came from other stars that blew up tens of millions of years ago. So it's a different place.
Question?
In the benefit of hindsight, are there any physical changes you would have made to the probe itself?
Well, there are a lot of things that Galileo did following Voyager and that Cassini's doing now following Voyager in the sense of much more advanced technology. The cameras we had on Voyager were Vidicons, tubes. And of course today everything's CCDs, that's what you have in your cell phone. CCDs are everywhere. They're much higher resolution, much more sensitive. It's a much better camera. So the technology on Voyager was the most available at that time in the 1970s, but that was more than 40 years ago.
But at the time, did you wish you had one thing on there that you didn't put on, or that you couldn't fit, or didn't have the capability for whatever reason?
Actually, there was something which was missing, but we didn't know how to do it in those days. So, see, that science instruments also evolved. So it turns out some important part of the solar wind which we can't detect because the instrument isn't sensitive enough. So there are cases like that where we didn't know how to build the instrument in a way that could be launched on Voyager.
All right, let's get one more question in over here, and then I think we're pretty much running out of time here. Go ahead.
Good
Or maybe we
evening.
can use
I'm
two
intrigued with NASA's mission to Europa in the future. What data are we looking for, and are we planning on landing? And if we are landing, how are we planning to get through that sheet of ice?
You should ask the gentleman that's about on your right arm, two over.
We don't have a lander yet. We have a mission, but no lander.
So Europa is a planned mission. I'm going to say this wrong though, so I don't know, Mike. Maybe you want to stand up and tell them what you've got. I really don't want to misspeak. I apologize.
Okay. Yeah, so I'm Mike Watkins. I'm the.
Go ahead and
you better go in front of the microphone if you don't mind, Mike. Yeah, as long as you're here.
I apologize, Mike.
Hollered into talking here. Mike Watkins, the director of JPL. And I'm here in the audience just like you guys are, marveling at these folks on stage and what happened when I was 10 years old or something when Voyager launched. It's amazing. And I will say that those images are why I do what I do, actually, quite seriously. The images from the Jupiter and Saturn flybys are part of why I went into what I did in grad school. But Europa, indeed, as Susie said, it's it's the grandchild of Voyager. And so our first mission to Europa, we cannot land. We're only going to fly by. So we're going to do kind of a, similar to what Voyager did. But instead of flying by one time, we're going to fly by 45 times. And so you might think we'd go into orbit around Europa, but the radiation is incredibly intense, and we'll be fried in about a month. So in fact, we go way far away, and we dive down and make a close approach and fly by Europa, and then go way away again and come back. And we do that 45 times. And we're going to image the surface. We have very bad pictures, even of Europa right now. There's a few swaths of about 10 meters, but most of it's hundreds of meters. So we're going to take 1 meter imagery of a lot of Europa. We're going to look at this, do spectroscopy, and try to understand why the ice has those weird orange streaks on it when it's supposed to be snow. It could be salt from the ocean seeping up. Look for any plumes and geysers that are there. And then we carry a radar. We carry a low-frequency radar, and that radar can actually get through the ice and bounce off the ocean and come back and tell us how thick that ice is. So that another mission, so we're going to launch this mission around 2022, 2023, the Clipper, the flyby mission. We hope to launch a lander by 2024 or 2025, and actually learn enough from the Clipper mission to do a lander. But it will be a long time before we get a submarine through the ice. But we'll start by, we'll get there someday.
All right.
Thank you very much.
Sure. Since we have one more question there, let's get that one in, and then we're going to call it a night. Thank you. But thanks for stepping in there, Mike. Good job.
Just a quick question about imaging. So imaging technology is getting better and better. And I was wondering if there any scientific value in trying to reprocess Voyager imaging, if assuming raw data exists.
Is there any scientific value in doing what?
Take raw data and reprocess it with current.
Like remastering an old record or something.
Yeah.
I think people have been doing that to the extent possible. I know that, let's see, I think someone took pictures of Titan and stretched them and actually could see surface features in Voyager images, but really, really faintly. Someone just recently produced a picture of the Enceladus plume seen in Voyager pictures. By the way, there's an interesting little historical footnote here that the scan platform seized up, as you heard. So there was a whole sequence of images that did not get taken, and among those were images that were meant to cover the southern hemisphere of Enceladus. So we might have found the tiger stripe fractures and maybe even the plume with Voyager if that had not happened. But anyway, thanks for your question.
All right, I got one final question here now. By my math, 136 years from now, there'll be another alignment of these planets. Will it be worth doing a similar mission then, or is this, we've been there and done this one?
No, it's absolutely worth it.
If we haven't been back to Neptune by then, at the rate we're going, that might end up being the case, then yeah, we gotta do it. We gotta get back to Neptune. That's what we gotta do.
Yeah, absolutely.
Mike Watkins, are you listening? Neptune.
Ed, what do you think?
Well, I think the planetary program really has moved into orbiting rather than flybys.
Right.
Clearly, Uranus and Neptune have never been orbited, so hopefully, well before that time period you specified, there will be orbiters around those two, because with orbiters, you can really study things up much closer, and you can study them for 10 years, like Saturn. It's the next step in exploration, and landing is then the follow-on for that.
Well, if they ever do this, I want you to be the project scientist.
Oh, okay.
All right. Thank you very much, guys, and congratulations.
Thank you.
Thank you. Great job. Great job. Very nicely done.
Okay.
Congratulations.